Welcome to part 2 of lecture 8. To start, let's review our fundamental waveforms. We have the sine wave, the square wave, triangle wave, and sawtooth. The sine wave is a sinusoidal waveform with all energy concentrated at one frequency, so no harmonics above the fundamental. It's also the fundamental waveform of all complex periodic waves. So here we see the spectrum analyzer, and it's showing a single frequency and it's showing the amplitude of that frequency. We also see an oscillogram that shows a sine wave, and here's what it sounds like. A square wave is a non-sinusoidal waveform that contains an infinite number of odd-order harmonics. Because it contains odd-order harmonics, it generally sounds very harsh. Here's what it sounds like. A triangle wave is a non-sinusoidal waveform comprised of odd-order harmonics that decrease in amplitude quickly as harmonic frequencies decrease. Although it's not purely sinusoidal, the relatively low number of harmonics make this sound similar to a single frequency, and the triangle form is starting to resemble a sine wave. A sawtooth wave is a non-sinusoidal waveform that contains even and odd-order harmonics, and here's what that sounds like. Equalizers are systems of filters designed to alter the frequency response characteristics of an audio signal. The three parameters of an EQ, or equalizer, are frequency, gain, and Q. You find the frequency, you can turn it up or down, and then you can adjust how many frequencies on either side of that frequency you're affecting. So with distortion, every sound that you've ever heard has been distorted. We never ever hear anything the way it sounded at the source. As soon as it leaves the source, the environment changes it. Then when it gets to our ears, the signal gets altered again in each of the three sections of our ear, the outer, middle, and inner. Nonlinearity and distortion are the same thing. It's any change to the signal. If the signal changes in any way in that system, it's considered to be nonlinear. A system that is truly linear delivers at its output terminals a perfect replica of the signal applied to its input terminals. Let's listen to an example of nonlinearity. Distortion is the alteration of the original characteristics of an object, image, sound, or waveform, or a falsified reproduction of an audio or video signal caused by change in the waveform of the original signal. Let's listen to a clip without distortion. Now let's listen to that same example with a mild amount of clip distortion. Clipping occurs when peak transients rise above the maximum level, shearing off the waveform that produces a square wave. Let's listen to the clip unaltered. Now let's listen to that same clip with severe amounts of clipping. Phase distortion is the change in the relative phase of waveforms. Examples can include interference of incident and reflective waves, time delays, and comb filtering. Let's listen to an example without phase distortion. Now with phase distortion. Comb filters are created by combining direct sound and early reflections from boundaries within milliseconds of each other. 1 millisecond to 30 milliseconds to be specific. Signals that are of the same frequency and close in amplitude create phase distortion that results in comb filtering. Let's listen to this dialogue in sequence. First, we'll start with the dialogue unaffected, then we'll follow up with a comb filter of 10 milliseconds, and finally a modulating comb filter, otherwise known as a flange.
Modern electroacoustics began in 1915. Modern electroacoustics began in 1915. Modern electroacoustics began in 1915.
The Doppler effect is a change in the pitch of sound as a moving source approaches or moves away from a stationary observer. As a moving object approaches a stationary observer, the frequency increases. As that object moves away from the stationary observer, the frequency decreases. This happens because as the object is moving towards you, the sound that gets to you has to move through an area of increased pressure in front of the moving object. This increased pressure causes the waveform to shorten, increasing the pitch. As the object moves away from you, now the sound to get to you moves through an area of lower pressure, which causes the wavelength to increase, which lowers the pitch. Reflections occur when waves encounter boundaries in a sound field. The angle of incidence is the angle at which waves approach the boundary. Angle of reflection is the angle at which the wave leaves the boundary. The angles of incident and reflection are always going to be equal. With reflections and interference, destructive interference is a type of interference that causes changes in the frequency response of the original signal. And this is exactly what you're going to be doing for your audio analysis project. You're going to be playing pink noise through speakers and recording it in various places in the room to measure this exact thing. Let's revisit this animation to see how a single wave travels through space when there are no boundaries and how that changes once we put walls up. And let's revisit this animation to see how sound from the direct source arrives at the listener and how it's reflected off of different boundaries in the room. Let's listen to some different types of reflections. We'll start with a drum loop, and then flutter echoes, early reflections, discrete echoes, and finally reverb. When waves move through each other, occupying the same space at the same time, they can and will interfere with one another. They can positively interfere or negatively interfere with the molecules in that space. An example of interference patterns happening in the brain could be binaural beats. This relates to the beat frequencies that get created when two frequencies play at the same time. Think about tuning a guitar and how you hear pulses or interference patterns as you get closer to the correct pitch. They say there are certain beats or interference patterns that create moods in us psychoacoustically. Constructive interference happens when two waves pass through each other and positively reinforce one another. The waves must be of the exact same frequency and amplitude if we want a perfect 3 dB SBL increase. Here's an example of constructive interference. Positive and negative peaks match, so the amplitude doubles. Destructive interference happens when two waves pass through each other and negatively reinforce each other. Waves must be of the exact same frequency and amplitude to get a perfect canceling of the signal. And here's an example of that. Destructive interference with the peaks and valleys, exactly 180 degrees opposite polarity. So we get a zero sum at the output. So remember we talked earlier in the month about the different ways we localize sound. Frequencies are a big part of this. Low frequencies have the ability to wrap around the head because of their longer wavelength. The sound hits one ear, wraps around the head, and arrives at the other ear about 0.7 milliseconds later. Our brain is actually able to pick up on this time difference and uses it as one method of localizing where the sound is originating. High frequencies, on the other hand, can't diffract around the head because of their shorter wavelength. So what happens is the high frequencies bounce off your face, bounce around the room, and get to your other ear as reflections, and your brain is able to hear the difference in amplitude from one ear to the next, and uses that to identify where high frequencies are originating. When two or more waves hit our head within 30 milliseconds of one another, the brain uses the first wavefront and combines it with the information gathered from the following wavefronts to localize a sound's origin. This has to be between 1 and 30 milliseconds. What happens if we go beyond 30 milliseconds is that we start hearing discrete or separate signals. A good example would be closing our eyes on one side of a large gymnasium and having someone bounce a ball on the other side. We would have a hard time localizing the sound because of the difference in time between the direct and reflected sounds. This concludes Lecture 8 and our final lecture. Thank you. It has been a wonderful semester. Please keep practicing your listening skills daily. We'd like to wish you all the best in your journey moving forward throughout this program. Please make sure to keep in touch. Here's my email address. It's brianh@fullsail.com. Thank you. Take care.